Hello, all you wonderful earth science kids out there. This is Mr. Johansson, and we're going to be looking at earth science lesson number 3. This lesson will cover density, water density, and we'll talk about graphing. So to start with density, we first have to talk about mass. Mass is really just a measure of how many protons and neutrons there are in an object. All matter is made up of protons, neutrons, and electrons. That's what every atom is made of. Protons and neutrons are about the same size and mass, but electrons are tiny. They're about 1/2000th the mass of other particles. So let's just ignore the electrons for now. Volume. Okay, if a cube is 10 centimeters on each side, we're going to be talking about this cube for a little bit. If it's 10 centimeters on each side and we want to know its volume, we need to multiply length by width by depth. This tells us how much space is filled by an object. Now, key thing is the units must be considered. Length, width, and depth will be measured in centimeters in our examples. Volume. So length and width, when multiplied, give us an area in square centimeters. That's centimeters squared. The area of each side of the cube, that's that 10 centimeter cube. The area of each side, well, 10 centimeters times 10 centimeters is 100 centimeters squared. The total surface area of the cube, well, let's consider it. If we laid it out, we'd have the 4 blocks of the sides, but we'd also have the top and the bottom of the cube. So that would be 6 areas. So 6 times 100 centimeters squared would be 600 centimeters squared. Now when we multiply length, width, and depth, we have a volume in cubic centimeter, because centimeter times centimeter times centimeter is cubic centimeter. So the volume of the cube, well, 10 times 10 times 10 is 1,000 centimeters cubed. The centimeters cubed shows us specifically that we have a volume, which would be a measure of space. Density is the ratio of mass to volume. It's really a measure of how many protons and neutrons are in a volume. In practice, of course, we use grams to measure mass and cubic centimeters to measure volume. So if we solve this for mass and volume, density equals mass over volume. And if we solve that for mass, just get mass all by itself, we multiply both sides by V. The V's on where their top and bottom cancel out. So we have mass equals density times volume. And if we solve this for volume, we end up with volume equals mass divided by density. Examples. So Felicity measures a cube to be 4 centimeters on a side. What is the volume? Well, it would be 4 times 4 times 4. So how do we do that? 4 times 4 times 4. Well, in your calculator, 4 times 4 is 16 times 4 equals, what do you get? 64. But we need to make sure we say cm cubed. She measures the mass to be 192 grams. What is the density of the cube? Well, density equals mass, which is 192, divided by her volume, which is 64. So the density comes out to be 3 grams per cubic centimeter. Narissa has a cube that measures a cube to have sides of 7 centimeters long. What is the volume of the cube? All right, well, 7 times 7 times 7 So 7 times 7 is 49 times 7 equals 343 cubic centimeters. If it's of the same substance as Felicity's cube, what is its mass? All right. Well, we know that if we're looking for mass, we have density equals mass over volume. We're looking for mass by itself, multiply both sides by V. So the V's cancel out here. So what is its mass? The density is 3 grams per cubic centimeter, 3 grams per cm3, and we're multiplying that by 343 cubic centimeters. Now the cubic centimeters will cancel out here, leaving us grams. So 3 grams times 343 cubic centimeters is equal to 1,029 grams. Tanika has 81 grams of the same stuff. What's the volume of her cube? Well, density equals mass over volume, right? We know that volume equals mass over density, okay? So 81 grams divided by 3 grams per cubic centimeter, that's going to be 27 cubic centimeters, right? It's kind of fun. And what is the length of each side? Well, how do you do that? Well, what times itself 3 times equals 27? You could just try a few different numbers, but how about, well, what's 2 times 2? 4. Multiply it again. What do you have? 8? That's not right. How about 3 times 3? 3 times 3 is 9. Times 3 again. What's 9 times 3? Hey, 27. So we know the length of each side must be 3 centimeters. Again, pretty fun stuff. Let's talk about relative densities of different phases. If the phase is a gas, the volume of that gas would be very high and the density would be very low. Gas takes up whatever volume the container is. If the same amount of stuff is a liquid, now the volume is quite low compared to the gas phase of it, and the density is quite high. If it's a solid, now the volume has become very low. It's shrunk down a great deal, and the density is very high. So the atoms are very far apart in a gas. They're much closer in a liquid, and they're positively chummy in a solid, really close in a solid. Now, except water. Water is the only substance that does not follow this rule. The solid form of water has the atoms pushed further apart than they are in liquid water. So we can ask, why is water most dense at 4 degrees Celsius? And the answer is brilliant. So the question should be, why does water become less dense as it approaches 0 degrees Celsius, as it's cooling down to 4 degrees Celsius? In other words, if it's hot water and it's getting colder, it behaves normally. The atoms getting closer together as they vibrate slower and slower. But as it gets below 4 degrees Celsius, now the atoms are vibrating slow enough so they start to grab each other, and they briefly form their low-density solid patterns. The atoms are locking into ice patterns, and then their vibrations break them apart. But at 0 degrees, they simply stop breaking apart. The solid form of water locks the atoms in arrangements that are farther apart than they are in liquid water. Therefore, they have bigger volume and lower density. Ice floats. Every other substance is more dense in its solid form. Water is very unique in that way, and think of how important that is on planet Earth. If ice sank when it froze, our lakes would freeze from the bottom up. Ice would form on the surface and sink. The lakes would freeze from the bottom up. And then in the summertime, the ice would already be on the bottom. It would be kind of insulated by the meltwater that would be on top. And I don't think the lakes, most of them, would ever defrost all the way. Not sure life would even be here on planet Earth. if it wasn't for this special thing about water. So when is water most dense? Look at it right there. 4 degrees Celsius, most dense. If I go this way, what happens to the water? Becomes less dense. If I go the other way, what happens to the water? Becomes less dense. Remember that fact. You'll see it on a variety of questions. Let's talk about some graphs. A line graph is used for showing how a measured quantity changes over time, distance, or some other variable. A bar graph is used to compare data about one thing at different times. And a pie graph is used to show how a quantity is divided into parts and to compare the parts to one another. A graph is for you. It's for you to visually take in information and make complete sense of something very quickly. So look at this bar graph. This would be rainfall for 1958. And, well, assuming that we have January is here, February, March, April, May, June, July, August, September, October, November, December. When do we get the most rain? And look at that. April, May, June. In the springtime, we get the most rain. And a bar graph lets you see that very, very quickly. That's the whole point. Look at this pie graph. Okay, so this pie graph shows you the elements in the Earth's crust by mass. So check it out. Watch how quickly you're going to understand something you didn't before. What element is the most abundant in Earth's crust? Bet you didn't know that. Oxygen. Any rock you pick up, almost any rock you pick up, by mass, it's almost 50%. 46% of that mass is oxygen. More than 25% is silicon. So the two most abundant elements are oxygen and silicon. You know what oxygen and silicon, if you combine them together and don't have any elements in it, make? That's quartz. Quartz is one of the most abundant minerals on the surface of the Earth, and everybody knows about quartz. The next most abundant element is aluminum, right there. Aluminum and oxygen, silicon, and aluminum, and just a little bit of metal atoms make up the most common element on Earth because it sops up the most common atoms you find on the crust of the Earth. And the most common element, or the most common mineral on planet Earth is the mineral feldspar, and it's an aluminosilicate. There you go, feldspar. So take a look at these graphs. So make 2 graphs for yourself. And the first, just take a guess. Make a bar graph of the amount of money you'll make at age 20, 25, 30, etc. In the second, show how you spend your time now. Remember, there's 24 hours in a day: sleep, school, TV, homework, sports, etc., whatever you do. Realize that the first graph, how much money you make, is really going to be influenced very strongly by the second graph, what you're doing right now. So the anticipated earnings, let's see. At age 20, oh, I bet maybe I'll make $30,000 a year. At age 25, maybe I'm going to be making $60,000 a year. What a raise. At age 30, I want to be making $80,000 a year. How about that? And how I spend my time. Well, if I spend 6 hours a day sleeping, how about if I spend more than that? If I spend, maybe 8 hours a day at school, and what else do you do? Maybe video games. Maybe you go for a walk. Maybe you're on the phone, whatever. But that's how you spend your time. And realize if you can make your school time larger and you're spending more and more of your time studying and working and making yourself smarter, you might make your earnings go up significantly. So That's what graphs could do for you. They could show you a lot of interesting things. So we draw a line graph of the number of students in the room at the beginning of class versus time. So we have this line graph, and then we draw the number of students. I have nobody for a number of minutes, and then just right at the end, so let me mark that. That would be the number of students. That's minute 1, 2, and 3. Here's the late bell right here, and yeah, that's when I have the kids coming in. And if I draw a line graph of the number of students in the room at the end of class versus time, okay, minute 1, 2, and 3, and the number. Well, as soon as the bell rings, pretty much everybody leaves. So if you chuckle a little bit at those line graphs, you understand what I'm talking about. And that's kind of the point. Graphs are meant to get the information into you very, very quickly with minimum effort. That's why we do graphs.